Okay. Let me see. So what last two are you guys talking about? Let me see.
42, 58.
In which section?
3.2.
3.2?
Yes.
All right, let's start there, and then I'll
Page 190.
do these questions. Page 190. Say the numbers again.
42 and 58.
42, 58. Oh, cool. I love this kind of question. So the 42 is this one. G of x is
X over E.
x over e of x. Fine. By the way, I didn't say this about really higher order derivatives. So you have f prime is the first, f double prime is the second, f triple prime is the third, and then you're just like, I don't want to get to the point where I have, and then you have to first count them to figure out this is the 67th. No, screw that. So we just go like that and forever after that. So a little parentheses means it's not a fourth power, it's a fourth derivative, fifth derivative. Thank God. Because I don't want to have little tally marks, 5, 10, 15, 20, it's a 33. No. So this says something very freaky. But whenever you see a problem like this, you know it's going to involve finding a rule, a pattern. So you should do like 3 or 4 iterations, and you should be able to see a pattern that you can capture. Whoa. Yeah. Oh, hey. Whoop. So, what I would do with this immediately is rewrite it, but it's up to you what you want to do with that. I don't know if you left it that way and attacked it with quotient rule. Is that the way you did it?
Yeah. Well, according to this section, we have to do the quotient because.
Oh yeah, you're right. We don't know chain rule yet. But that wouldn't even involve. Well, yes, it would technically. Oh, well, too bad for us. So G prime. What does quotient rule say in this case?
Well, we say the derivatives of f. The denominator.
Good. Top first.
Yeah,
top first. So derivative of x is 1 times the bottom.
To the power x.
Minus
x dx.
Good. The top times the derivative of the bottom, and you can't beat e to the x for derivatives over
E to the x
squared.
And you can factor out
e to the x squared. I like it. How can you simplify that?
Factor out e to the x and cancel 1.
I like it. So 1 e to the x can cancel. Are we all on the same page?
Making sense.
So 1 e to the x cancels everywhere. So I end up with
1 minus x.
good. 1 minus x over
Yeah.
e to the x. Okay, so it's not enough to establish a pattern, but you might even start to realize maybe that 1 has something to do with the first derivative, maybe. I don't know. It's not enough to go on yet. So just keep going. What do you get for the second derivative? What happens?
We get 2 minus x to the power over dx.
Yeah, let me get there. So if you, what's the derivative of the top?
Minus 1.
Yeah, negative 1 times the bottom
Dx.
minus the
Dx.
top
EX.
times the derivative of the bottom. Are we all cool with that? That's the quotient rule. All over
Yes.
e to the x squared. And again,
Take the common out.
so then if I get all my stuff together, this is negative 1 minus 1.
Minus 2.
Negative 2. And then minus and negative x plus x over
Yes.
e to the x. Sorry. Okay, now we can even maybe stop and get the pattern now, but let's just do one more to verify. Just because this is so much fun. So if I do one more, so now I'm focusing on this, it would be derivative of the top is
Plus 1.
is 1 times the bottom minus the top times the derivative of the bottom, all over the bottom squared. Again, one of them dies.
1 minus
So 1 minus negative 2 is 3, and then minus x. So actually I can look at, this is actually negative 1 times x minus 1. And this is x minus 2. And this is negative 1 times x minus 3. You guys see that? So I think for some of you guys, if you did this problem, you might have been able to see the pattern, but you weren't sure how to capture the alternating thing. Okay, that's true for one of you guys. But what's the basic? Forget about that negative 1 thing. Like it's not even there. What's the GN look like?
It's x minus n over a dx.
Yeah, so it's x minus
N.
which derivative I'm on. Does it make sense? For the second derivative, it was a 2. For the third derivative, it was a 3. So it looks like it's going to be x minus n over
dx.
u dx. Now, it's not quite right, of course, because every other one is negative. And the way you capture that is, I love it. And you just make sure that the power, so it was negative 1 to the n, does that work correctly? So for the first derivative, it would be negative, right?
Oh, yeah.
And for the first derivative, it is negative. Now, of course, if the first derivative is positive and the second derivative is negative, you could just make it negative 1 to the n plus 1. That would offset it. Does that make any sense?
Wait, can you repeat that one more time?
Sure. One of the most simple function you can get that will alternate if you're increasing its exponent or just changing something in it by 1 every time would be negative 1 to the n. Because negative 1 to the first is negative 1.
Right.
Negative 1 to the second is 1. So
Yeah.
So the real question is, do I want to represent it like this, or do I want to represent it like this? And that really just has to do with when is it negative, when is it positive.
Okay.
In this case, it was negative on the first go. So which one of these would be negative when n is 1? This one would be, right? Does that start to make some sense? So anytime you have an alternating sequence of things, you can capture that alternation by one of these choices. And you just choose the one that matches when it's negative, when it's positive. Cool. So then this will be negative 1 to the n times that business. Yes, sir?
Does the negative 1 to the n go in the numerator, or is it just in front of everything?
Both of those are the same.
Okay.
Yeah, because it's like over 1. So yeah, you could write it like this, which is a little more like how I write these. I like that. That even looks a little cleaner. So yeah. Sweet. So now, whenever you see a function, whenever you see a question that involves find the nth this thing, don't go, what the freak am I supposed to do? Just do several iterations, and it's supposed to be a pattern that you can see. Right, so e to the x and the sine and cosine, they're cyclic, so they come up with these kind of patterns that you can find all the time.
The n is just however many times you're getting.
Yeah, so for the first derivative,
So if it's to the.
it was a 1 there.
So if it's
For the 0th derivative, it was a 0, right? It's kind of neat, so it actually kind of works backwards there too. But for the first derivative, it was a 1. For the second derivative, it was a 2. Cool. And it'll always happen because you always have that first 2 that's going to lose its e to the x, and it's going to be that 1 piece that's going to add on to the number. So it's always going to go up, 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 each derivative you take. Hopeful. Okay, and you can always do more if you don't see the pattern right away. You can do a few more. All right, so what about 58? Let's see. Oh, okay. 58 is not calculation heavy at all. It's concept heavy, right? They're actually trying to get you to explain what the hell these calculus things would mean. Let's see. A manufacturer produces bolts of fabric. 58 says I've got Q yards of fabric blah 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 sold, that is sold. It's a function of the selling price P dollars per yard. So it's not just the price, it's a dollars per yard. It's a price per yard. All right, so then they tell you that the amount of fabric sold is a function of the price, which makes sense. I mean, that's very basic business understanding. Total revenue earned. So if this is the amount of yards, the yards of fabric you're selling, how would you figure out how much money you actually make? You multiply the yards you're selling by the price per yard. Right? So the revenue function for this would be P times F of P. Okay, so that's the setup for this problem. Right? Then they say, what does it mean to say F of 20 equal 10,000, and F prime of 20 equal 350 mean.
That's a negative 50, I think.
Say again?
Negative 350.
Oh, yeah, thank you. So what units is the output of F in? Yards, because the output of F is Q. Q is yards of fabric. I love it, right? So, and what am I taking the derivative with respect to? This is why this should maybe even be better to represent with Leibniz notation, right? What is this prime hiding? What am I taking the derivative with respect to? What's the variable assumed to be here?
Cost.
Well, yeah, price.
Price.
So then this would be df dp. Is that cool? So that's what that prime hides. You take a derivative of that f with respect to price. So really, that's what I'm curious about. If I change the price by a little bit, what's going to happen to eventually to my revenue? But right now, this is just what's going to happen to the amount of fabric I sell. You with me? So if I increase my price, I'm probably going to sell less fabric, but I might still sell enough that my revenue goes up. So who cares? How we know so far? So this first piece should be really easy. What does that mean? 10,000 yards if 10,000 yards will be sold if
20 bucks.
if I set it at $20 a yard. So F of 20 equals 10,000 means if I set my price to $20 per yard, I will sell 10,000 yards of fabric. How we doing so far? And that's just from this definition here. F evaluated at the price gives me the amount. Bam. So that's pretty easy. Here's where it gets more freaky, because this is applying a process to this well-known thing, and then we have to interpret what the hell it means. But what did I just say? Let me do this over here. So everybody got what they want from that thing? Good. It's also recorded. So here's why Leibniz notation kicks so much ass, because df dp, you guys told me what's f, what units are f in?
Dollar? No yards.
F is q, q is yards. So that's the change in yards. And of course, what's units are price in? Dollars. Per change, so the change in yards for every change in price. This is dollars, and this is obviously yards. So it tells me if I changed my price by so much, the equivalent change in yards that I would get. Is that cool? So this part tells me what price, how do I want to say this? This is the derivative. So that tells me it means yards per price in a way, right? And of course, it's price per yard, but let's not get all freaky. So if I have it at $20 per yard, and I change that by a little bit, by the smallest little amount, how much will my number of yards that I sell change? So let me try this again. If I change the price by $1, how much will my number of yards change? 350. That's negative 350 over 1, right? So that's exactly slope. If I move over 1, this goes down 350, and this represents the yards that I sell.
Were we given that, or did we figure that out before? It was given.
Given which piece, I'm sorry?
The negative 350 over 1.
Oh, that's given.
Okay.
Yeah. I can't figure it out because I don't actually have any function to work
That's
with.
why I was curious.
That's all right. But you guys see that? And that's why this notation is really good for units. And whenever you have a question like this, you have to answer according to units, and the units keep you straight. So it's better to write it fully out in Leibniz notation because there's the units. It's a little freaky because of the freaking F, but you always got to go back, oh, that's yards, right? So this means that if I increase my price that I sell it at to $1, if I moved it from $20 to $21, the yards of fabric that I sell would go down by 350. So I'd sell 10,000 minus 350. And let me say this, that's roughly, because this exact number only holds for exactly 20. The minute I move a little bit, that number's going to change. That's the whole idea of derivative, of course, right? I have a derivative at a point. So if I make a big change like $1 change, that's kind of a big step to take.
So then the slope changes, so then how would you be...
So what you do is you can say this is not approximately. You can make if I change it by a penny, then this would change by 3.5 yards. Then that's much more true because I'm not letting it go that big of a step.
Gotcha.
It's still a relatively big step related to infinitesimally small step. But it's a pretty small step to change it by a penny. So that's pretty decent. Are you guys kind of with me here? Okay, maybe. All right. And then part 2 says, or part B, assuming the values in part A, find R prime of 20. I love it. So we know R of P is PF of P. We know F of, let's see, what else we know? We know F of 20 is 10,000. We know F prime of 20 is negative 350, right? That's the stuff we definitely know for sure. And somebody's like, what the hell is F? Right? Or some variation on that. But you don't have to know what the hell F is. What are they asking me for in part B?
Substitute.
What are they asking me for? What's the question?
R prime, right?
R prime at 20. So if I can figure out what R prime of P is, I can then plug a 20 in. So just from this, and I don't care that you don't know what that is, because I don't know what that is either. But I know how to do a function times another function. How would I do that derivative? All right. So what's the derivative of P?
P prime.
Yeah. Times
Which in this case is?
constant, which is 0.
Which is, no, it's not a constant. It's a function. It's like x.
1.
So I really want you guys to realize P acts like x here, because that's my input variable. You with me?
1.
So the derivative of P would be 1. Just like the derivative of x would be 1 if I'm taking the derivative with respect to x. How we doing? Another way to think of this is derivative of P with respect to P, well, that's freaking 1. It's a ratio of something to itself. Right? So that's 1 times F. Right? That's the first piece of product rule, plus. What's the second piece?
We'll give P down.
Yeah, leave P alone, and they each get a term, right? So leave P alone. And now what's F? What's the derivative of F of P?
We are F minus.
No, we don't know. What's the derivative of P? F prime P. You gotta look. All right. Because you don't know what f is, so you're just putting what it would be in there. It would be whatever the hell the derivative is. That's what it would be. Now, I want to know what r prime of 20 is. So you just plug a 20 in, and you know everything you need to know. All right. So I'll leave that for you to finish up. I'll leave the really easy part for you to do. This is freaky. I understand, because when you first see this, you're like, how am I supposed to do anything with this? I don't know what f is. But they give you this kind of information. You don't have to know what the function is, because they give you everything you have to know at the point 20. So you don't have to know what the whole function is, because you're only interested in at the point 20. So you just plug that in where you need it. Yeah?
So, hold on, we don't know what's f prime of p, but what's f of p?
We know what f of 20 is.
Okay.
So when I plug a 20 in for p, f of 20, I know what it is.
But don't we also know what f prime of 20 is?
Yes, we do.
Okay.
So when I plug a 20 in there, I know what f prime of 20 is, negative 350. So that's why I don't need to know what the whole f of p is. I don't need to know what the function is everywhere. They only have to tell me what the function and the derivative were at 20. That's all I need. And actually, that's pretty close to real life, because in real life, we have observations that I don't want to take the time to try to fit a function through. So I do this kind of work here, exactly this kind of work, and then I throw my observations at those points in. And then I can do more with it. I don't actually have to need a background function to work with.
So P will be 20?
Yeah, P is 20.
No, the other.
Yeah, P is 20.
Yes.
Wherever you see a P, you put 20. Because that's what I know that value is. Yeah.
So for f of p, we're going to put 10,000 because that's...
Well, you'll put f of 20 plus 20 comes f prime of 20. That's 20. That's 10,000. That's negative 350. Cool. Yeah.
It says interpret as well. So what does this change mean as far as the revenue?
Yeah, so they mean this piece by itself. So if you know what this meant, we can figure out what that means. And again, what units will this revenue be in? Considering that it's P times F of P, this is yards, this is dollars per yard. So it's exactly what revenue should be in. Dollars, right? So what's R prime of 20 represent? What's R prime represent?
The revenue.
No, R represents revenue. What does R prime represent?
Change in revenue?
Change in revenue per...
$20.
From the R?
No. What am I taking respect to? What's when I write R prime of P, what would it look like in Leibniz notation? DR? DP. You with me? So it would be the units for it, which is a really good place to start with any interpret question. The units would be dollars per... What's... P is not yards. So it's the change in revenue, which is in dollars, over the change in price, which is also in dollars, which is fine. We get that all the time, believe it or not. So it's how much it would that number you get here would represent if I did change my price by $1. I would expect my revenue to change roughly by whatever this comes out to be. I would expect to get that much more or less money, depending on if it comes out negative or positive. Okay, maybe. Okay. So many of you are like devoid of emotion. It's freaking me out. I'm ambivalent about that. Okay. So I got a few questions from 3.3 and 3.4.
Can we look at 24? 3.2?
Second?
3.2, 24. I did apply the ocean rule, but for some reason it doesn't work right now.
3.2, number
24.
24. Okay, let's see. So they say find the derivative. They say differentiate, which is another way of saying find the derivative. Yeah, and then you just directly attack this with quotient rule. It's not a single. If it was a single term at the bottom and I can do whatever I want to, I would just split it up. Then I don't have to use quotient rule, right? Not a single term at the bottom. Damn. Okay. So f prime. Let me do this all the way out. Let me show you, because trust me, when they start getting more complicated, and I've said this before, you want to write the rule first and then attack the derivatives. You don't want to try to differentiate as you go. So let me show you what that would look like. You guys help me with the rule. What do I differentiate first? Good. Top first. That's my song for this. Top first. Times the bottom. Minus. Good. Derivative of the bottom times the top. All over. Bottom squared. Okay, so now we can. That's the rule, and that looks like a prime. Let me get rid of that. So I've written the rule. Now I can attack the derivatives, and it's kind of nice for your brain to worry about the rule first, because they're relatively new anyway. So I got to what's the rule, and then worry about the derivatives. So what's the derivative of what's going to happen in here?
Product rule.
Product rule. Love the one, of course.
Zero.
Just dies, poor little dude. So then if I do the product rule, I get good, negative 1 e to the x. So derivative of x, and then this plus negative, so it's going to be another minus there. Is that cool? Leave x alone. Derivative of e to the x is, of course, e to the x. Good. So that's that piece. Can I just erase all this so you guys got this here? Okay. That's nothing they didn't have in there already. Anyway. How are we doing so far? Where'd you go? What was it? Great. So good. So, what about this one? 1. And then derivative of e to the x and e to the x. Then you got 1 minus x e to the x. That's the leaving the first dude alone. All over. Please, dear God, never foil this thing out or anything, right? No point to it.
We have complicated quotient rules. How cleaned up do you want them on the test?
At least one more step beyond this.
Okay.
Right? Don't stop here, because there's almost definitely going to be some like terms.
Okay.
Beyond cleanup, which is just distribute and like terms, you can stop wherever the hell that gets you to, because what you do next really depends on what you do next with it in the problem, right? Is the problem set it equal to something else? Is it find the zeros? Is it something? Then the form totally depends on what the hell you want to do with it. But at least clean this thing up. So when I distribute this, we get off. Is that cool enough? I mean, who asked that question? Where am I at? I can do like my calc teacher said, the rest is algebra. Leave me alone.
What?
The rest is algebra.
Oh.
So why would I waste my time showing you? Yeah, I mean, you should be able to finish that up. That's what I'm trying to say. Just foil. Careful with the minus, of course. Get your like terms together and you're done. Okay. So let's go to 3.3. I got a question on 34 and 35, is that?
Yeah.
And real quick, there is one thing I didn't explain. Tangent line is the line that shares the same slope at that point. Normal line is the line that everybody's comfortable around. No, it's the line that is perpendicular, exactly. So normal is just another word for perpendicular. There's actually several words for perpendicular you'll learn as you go higher through your math courses. Okay, so if I know the slope at a point and I can get the tangent line, I just take the perpendicular slope. And how do you find the perpendicular slope?
Inverse.
Negative reciprocal. I like it. And what I like to tell my students is parallel is exactly the same, perpendicular is totally opposite. So don't just change the sign, also flip it, right? So negative reciprocal. So that the reason I'm saying that is number 34 says find both of these for this function at this point. So if you haven't done this yet, take a second and find that derivative. If you've already done this in the homework, there's no point doing it again. I don't know if this is homework. Is this homework?
34, it's not 34, I think.
Did you want 34?
Section
Section 3.3?
34, yes.
Oh, am I doing 3.2? I am so smart. All right, well, that was still interesting. But, I mean, if you do this and you find the slope, now I kind of want to do it.
4x squared.
So you get 2x squared plus 2 minus 2x times 2x, so 4x squared, right? So it'll be twice this minus 2x times 2x over x squared plus 1 squared. So it'll be negative 2x squared plus 2 over. So to find the tangent line, you'd find m equal to f prime at 1. Cool? So that would be 0, it looks like.
Yep.
All right, well, so what's m perpendicular then, at least symbolically? Or actually, even better would be
Y equals 0.
undefined. So obviously what's happening at 1, 1 on that graph, does somebody know? I mean, that pretty much tells you. The slope at that point is 0, so it's horizontal at that point. So the normal line would be a vertical line through that point. So it's almost too easy then. What's the horizontal line going through this?
Y equals 1.
Yes. Horizontal y equals. Vertical line going through this? X equals 1. Right? So the tangent line is y equals 1. The normal line would be x equals 1. Right? All right. So that was completely unnecessary, but I felt like I had to finish it. So let me get to the real question, which is in section 3.3, number 34. I like that. You're very diplomatic about it. I'm not sure if that's right. So this is a combination of cyclic kind of functions. So for what values of x does the graph of f have a horizontal tangent? So that's going to happen a lot. Finding out where the derivatives equal 0 is going to be a huge part. Right? Which makes sense, because that's where things kind of happen. You know, that's like the highest the unemployment got, or that's the lowest cost for producing something, whatever. So of course, in order to answer that question, you first have to take the derivative, which involves a product rule, right? So do that real quick. Don't say anything out loud.
Minus e to the x. Sine x.
So if you do, yeah. So I would do the derivative of the first times the second. And then the derivative of the second times the first. Derivative of cosine is negative sine. Good. Just remember, this will get you through all this. The derivative of the cos stuff is always negative. That kicks ass. Okay. So how do I find out where this goes horizontal?
Zero.
Yeah, so set this equal to 0, which will take you back to your pre-calc days. Well, I like that. We just learned 2 minus 5. Now let's look at
Take e to the x common.
second.
E to the x is common between those two.
I like it. I can even kill it. Why can't I just divide by it?
Because when you factor out, you said equals 0, it's not 0.
E to the x can never be 0, so I'm allowed to divide by it whenever I feel it. And I felt it right there. So then I guess cosine x minus sine x equals 0. How do I solve that?
tangent, we can remove sine to the other side, and divide by cosine to be tangent equals to 1.
I like it. So you can take sine over here, right? And then you could divide by cosine to make a tangent, or you could, you know where cosine x equals sine x.
45.
Yeah. So it equals, these two equal each other at the base angle would be pi over 4. And where again are they equal? You gotta be careful. Are they equal in the second quadrant?
First and third.
Good, first and third. That's where they would share the same sign. So I know the 45-degree angles, they are root 2 over 2, but you gotta be careful about the signs. So the third quadrant, how can I just capture that? It's gonna be first quadrant, third quadrant. First quadrant and third quadrant. And so I can just put pi over 4 plus, how far do I want to go?
K pi?
It's just pi,
It's
right?
just pi, yeah.
Half a rotation is pi. Cool. So plus pi, and you can use k or n, I don't care. K was the one we used in pre-calc. Do you guys remember that from pre-calc? Solving trig equations very often involves infinite number of answers.
If we took e to the x equals to 0, can we say x would be to negative infinity, would be the horizontals?
Oh, I see what you mean. That's good. Well, the limit, so what you're saying is the limit as x goes to infinity, negative infinity, of this,
Equals to 0.
and you can think squeeze theorem, but you don't have to use squeeze theorem. I mean, this is bounded, and this becomes 0. So this is 0. But is that a point that I can give as an answer for where this has a horizontal tangent? No. So you can't say at the point negative infinity. You could, I'd love it if you just said something like this. I realize that this is true.
We can take e to the x outside from the first equation. And then equals to 0, or cosine minus sine equals to 0.
This is true. Now, if I do that, technically this never equals 0.
Yeah.
In the limit that x goes to negative infinity, that's 0.
Can I say that?
But this never equals 0. So I like what you're thinking. I like what you're at infinity.
At infinity.
And negative infinity, sorry.
Yeah.
This would have a horizontal tangent.
Yeah.
I can't get there. So I can't include that in my collection of points where it's horizontal. Does that make sense? I like the fact that you saw that, but you can't get there, so you can't include it in a set of points where it's horizontal. E to the x is never horizontal itself. Never. You could say at negative infinity, but you just can't get there. Okay. How's that? Is that cool? Yes, sir.
That's 3-3 and that's 3-1.
This was 3-2, yeah. Sorry. This is 3-3. Okay. I had question 35, which looks very physicsy, like that. Let's see. I've been doing too much of these all the way out. Maybe I should just get you started on this. A mass on a spring vibrates horizontally on a smooth, level surface. So it's moving back and forth. Here's your x. Blah, blah, blah. Its equation of motion is x of t equals sine 8 sine t, sorry. T is in seconds, x is in centimeters. Alright, find the velocity and acceleration at time t. Find the position, velocity, and acceleration of the mass at time t equals 2 pi over 3. So what would you do with this? The velocity function would be how related to this? The derivative. So you take its derivative. The acceleration would be the derivative of v, which would be the second derivative of x. Right? So what's the derivative of x of t?
8 cosine.
Yeah, sine goes to cosine. I like it. So 8 cosine t.
and then -8 sine t.
-8 sine t, I love it. So now part A says, and that's part A. Find the velocity and the acceleration at time t. Done. Part B says, find the position, velocity, and acceleration at time t equal 2 pi over 3. So you just plug a 2 pi over 3 in there, and there. Notice something very strange about the function that they've set up for this. The position is actually, whatever value the position has, is actually the opposite of the value of the acceleration. Yeah.
I did that, I got only one answer, while I think in book he gave 3 answers.
Oh, it's just because, you mean 3 answers for all?
Yeah, because I have -4 square root of 3, the only answer I got, but I think
Well, it's because they ask you for the position,
it's plus
the velocity, and the acceleration. They ask you for the position, so you got to do x at 2 pi over 3. You got to do x prime at 2 pi over 3, and you got to do x double prime. So you should get 3 answers. Of course, these two will just be off by negative sign, but you still get the 3 answers. And what's really important there is units. Right? Obviously getting the right number there, but don't forget your units. So on a test or a quiz, do not forget your units. I will make sure that every problem has some units on it. If you forget your units, I've got to take points off. It just sucks so bad.
Your physics is coming out.
Yes. But it's even more, to learn a subject, you should not only be able to do the processes involved, but you should be able to explain what you're doing. And part of explaining this is, what units are you currently in? Whenever you do some calculus thing to it, what units are you in now? So, of course, the units on this would be,
Centimeters per second.
well, for this one it would be centimeters. For this one it would be,
centimeter per second.
good, because the Leibniz notation for this would be dx
Over dt.
dt, so that's centimeters per second. And now this is where it gets a little weird. The Leibniz notation for this
TV
is d squared x over dt squared.
per second.
Yeah, so this is where it's centimeters per second squared. Just because it's the change in velocity, that's velocity, per second. So it actually comes out to centimeter per second squared. That's acceleration. It's pretty much always length per second, per time squared. But it's just, that's the math that's kind of screws up. This is the one place where math kind of screws up understanding. Is weird. Is that, what the hell is a square second? Right? What is that? What kind of universe does that look like? Right? I'm not all the way around my second yet. What does that mean? But this makes total sense. This is how every second, how many centimeters per second did my velocity change? That's the concept. Here's the math going, oh, I can rewrite that in this form. Thanks, math. Yeah.
I guess it's kind of basic, but how do you write the Leibniz notation based off of like a function or something? I just missed that, I guess.
It's so in this case, you look at the what's the actual variable,
Okay.
and what's the output.
Okay.
So when you do it, it's going to be d function over d variable, and then you just look to see how are those defined.
Okay.
So to go to the units.
Okay. Yeah,
Cool.
thanks.
How are we doing so far? Is that decent? Okay. And let's see, the last question I had up here was from 3.4. And 3.4 is where I want to spend some time here at the beginning. Anyway, let's see. Number 24. Oh, good. You're good. All right. So let me put a little asterisk next to 24 in 3.4, because there is one piece of 3.4 that I haven't officially done yet. But it's in the reading. So anything else from homework? Yeah.
18 on 3.2.
Yeah, this one is evil. Let me write this down, and you guys tell me why this is evil.
Because there's two,
The constant?
It looks like there's two variables, but pretty much k, unless stated otherwise, will almost always be a constant. we currently do not know how to handle a multivariable function. Probably because this is called single variable calculus, right? But you'll talk about like partial derivatives when you have more than one variable, and you actually have to be very specific. At this moment, I'm talking about this variable, or at this moment, I'm talking about that variable. That's when Leibniz notation becomes stupid important. If you have multivariables in it, which variable are you taking the derivative of? Oh, shit. So the prime just is never used when you get to that point. So here, k is a constant. So now you can attack that with, this is section 3.2, so you have to do quotient rule. You can't really bring it up and do chain rule. Is that cool? I don't know if that was the issue. Was that the issue? I think it was one you asked me.
No.
Yes.
Oh no, it was one you asked me. Sorry. I got one more to finish for you eventually. Does that, I don't know if that was the issue, the several variables? But this part is really not a variable. So what would this look like to start? We do it even like this. dy ds. Because s is the variable. K is a constant. They were just very evil. That's actually pretty damn evil. Right? How do you... You're supposed to really know that k is a constant. They should tell you. How would this look? What's really nice about the first piece? Derivative of 1 is 0. So you get 0 minus the top times the derivative of the bottom. Now what's the derivative of the bottom going to be?
1 plus k dx.
Good. 1 plus k, and of course the derivative of this is just itself. Over this thing squared, and I'll let you, really just-
Why we don't consider k e to the power 5 as
It's an s, sorry.
product rule?
Because k itself is a constant. K is a constant. Two things. Maybe just one thing. You could not do this problem at all in this class if k itself was actually a variable. You just couldn't. We don't know how to deal with multivariable functions yet. So that pretty much eliminates both s and k being variables, but it's evil of them not to specify which one was the constant. So this is just like 5 e to the s. So that derivative would be 5 e to the s. Yeah. Is that cool? Okay. So here's the one thing that I left out of this section was once we learn chain rule, we could actually learn. So of course we know the derivative of e to the x is e to the x. But what's the derivative of anything else to the x? Some other base besides e. And I don't know if you remember, we already talked a little bit about the fact that anything else there, it's going to be some multiple times the thing. We got to figure out what the hell that is. So let me see if you guys, let's analyze this a little bit. Does anybody know how to rewrite this using logs? No. Don't rewrite this whole expression. Rewrite this piece of it.
You say x log a, right? Say x log a, right? Or no? X times log of a.
So let me ask you this: if I took, if I had a to the x sitting there, and I took the ln of it, what could I do?
Move the x right over to the front.
The x comes down, right? Now I can't just take ln of this side. I have to take ln of that side, and we're going to talk today about what to do when y isn't solved and you can't solve for y. It's called implicit differentiation. We're doing that today. Yay! So I don't want to take the natural log of both sides. I want to do two things to this side, so overall I didn't do shit to that side. So if I take an ln, I better at the same time, what's the opposite of
E.
E? Now how do I just throw an e in there? Of course. You're crazy. So if I do that, isn't that the same thing as a to the x?
Yes.
So if I rewrite this as e to the ln ax, that's the exact same thing.
Mm-hmm.
That is like, when you see that, you're like, why the hell would I ever do that? Well, here's one reason. Now I can bring the x down, like you guys told me there. And now you can take this guy's derivative. Do it. What's A? What's A? What is A? It's a constant, just like 2 or 5. So you can do this. I'll do part of it for you. Derivative of e to something is itself. And then what rule is going to come into play?
Chain rule.
All right, so do it. Try to do it. Do that guy's derivative. Have faith in the rule. Write the rule first. Right? Take the outside function, which we just said is e, so times whatever the chain rule says. So, chain rule says derivative of the outside function first, so that's itself, with that thing still in it, times the derivative of this, right, that's chain rule. So that's writing the rule down. The rule says derivative of the outside function times the derivative of the inside function. So then, what's the derivative of this?
Ln
ln a, right? Because this is just like 5x, 6x. Right, so derivative of 5x would be 5. Derivative of ln a x would be ln a. Now, what was this again?
A to the x.
A to the x, 11. So if I have f of x is a to the x, f prime of x is a to the x ln a. So of course, if a is e, the ln of e is 1. Are you guys here? It's a holograph. Could I just put my hand right through you? Ln of e is 1, of course, because those are inverse functions. Okay, cool. So now this is a rule you must know. So let's do a couple quick examples. If I have g of x is 7 to the x, what's g prime of x going to be?
7x ln 7.
Yeah, it's almost too easy to believe. You just got to remember it. It would be itself, just like e is. I mean, anything to a power should be like e, basically. It's just that if they're not e exactly, they have a little correction term, which is ln of whatever the hell that base is.
So why are you using 1 again then? I'm missing a little bit here.
Just really because of this.
Okay.
That's exactly why I must use ln. Because this is the only way I can take the derivative of this.
Listen. Okay.
So I use the fact that we know what the derivative of e to the x is. We know what that derivative is, so I want to use that fact to figure out what the derivative of anything to the x is.
Okay.
And in order to use that, I had to introduce an ln in there.
I have a question.
Yeah.
Can you explain again how did you get ln a to the power x this one? This one.
Here?
Yeah, how did you get this?
Oh, what's the derivative of x times a constant? The derivative of x times a constant is the constant, yeah.
Yeah, you were missing the x ln a and I got confused over that.
Okay, cool. Because that was the derivative, yeah, good. Yes?
Can you explain again how it went from gx to g prime x? I'm not really sure why we ended this ln 7.
Oh, so this work here set up this rule. This is the rule for any exponential function where the base is not e. Right? Actually, this is a rule for when the base is e because it would just make this piece 1. That's another reason why it's its own derivative. Any other base is going to have that little correction term actually show up, not be 1. Right? So I don't know if you guys remember, but we were talking about any exponential. The slope through here is actually directly related to the log of the base. So we said if it was 2 to the x, we got like 0.69 as a piece. And if you do natural log of 2, If you did, you would get 0.69 blah, 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 blah. Okay, I don't know if you guys remember that at all, but that's what we talked about before. So now, this is a rule I have to apply. Yes, sir?
Can you do the second derivative of x?
Sure. So the second derivative, the really nice thing with the second derivative is this is a constant. So I know the derivative of this would be what?
7x.
This.
Yes.
And then you have the natural log of 7 just sort of sitting out there. So you end up with 7 to the x, natural log of 7.
Good question.
So then I could ask, that would be a good question to ask, like g n x, the nth derivative, right?
So that power is just going to keep on increasing no matter.
Exactly. So the second derivative is that squared. Third derivative would be that cubed. Because every time I do it, I'm going to have a natural log of 7 popping up.
Can you get rid of the natural log at all?
No. Well, your question is interesting because that is what it is.
You can't do
So there are situations we're going to learn later when I don't want it to look like that, so I do have to think ahead as to how I'm going to kill it. When we start talking about anti-differentiation, anti-derivatives. Let's not worry about that at all yet, because we're still talking about derivatives. All right. Oh, so now let me do that problem that I just erased. So let me, before I forget, it was 24, right? In section 3.4. So here, you guys, all right, I love it. This normally means it's ugly. All right, take the derivative. Just to make sure everybody's on the right track, what rule we have to use?
3.4, right?
Chain rule.
Yeah, 3.4. Chain rule. You have to use chain rule on this.
I have a question.
Yes.
G of x, 7 to the power x to an x, then 7. So if you're taking the second derivatives of the first derivatives, doesn't it look like a product rule?
Is this a function of x?
Okay.
Good.
Constant.
So it's a constant. It's a weird-looking constant. We're normally used to. It's a coefficient of this function. I just wrote it back there because it's easier to keep track of back there. But it's just like 5, 2, right? It's just an ugly number, an ln7, right? Not making a value judgment on its aesthetic value. So I really want you guys to start looking at a problem like this. I know what the derivative of 10 to the something is. What's the derivative of 10 to the something?
10 to something.
10 to the something.
Times ln something.
ln 10. I like it. So the derivative of 10 to something is 10 to the something, ln 10. But why is there more involved here?
Because there's a embedded
A more complicated function than just x up here, so it has to get its term. Times the derivative of 1 minus x squared. So this is all the derivative of the outside function. Bam. And then you do times the derivative of the inside function. So when I look at this, I don't even care what the hell that is. Part of my brain says it's more than x. I'm like, I know, I'll do chain rule in a second. But it's 10 to something. Okay, 10 to something, ln 10. Times, now I care what the hell you are. Right, so to finish this out, I get derivative of this is negative 2x. And there's really no really great place to put that. Out there, you have to kind of be careful. Because it sort of starts to look like scientific notation. How we doing so far, Zach? So chain rule doesn't care. It says I can be any damn where.
So is that about as simple as you're going to be able to make it there? Or simplified, I guess?
There's really, there's nothing you can do. Except, I mean, if you wanted to play around with change of base on that, you can flip-flop on who's the base and who's the argument. But who cares, right?
Okay.
If you forgot change of base formula, then you can't, so just leave it there. Okay. How do you feel now? So, I could have a quotient that involves 3 to the x. I could have a product that involves 7 to the 5x or whatever. All the rules still apply. You kind of with me? The other rules don't care. They still work the same way. Maybe. Okay. So anything else from 3.4 before we get into 3.5? Of course, if you were not here last time, I desperately ask you to watch the video. I'm not going to re-derive the chain rule. I did it once. All right, that's plenty. So if you weren't here last time, you really need to watch the video to at least see where the hell this rule comes from. Chain rule is one of the easiest mistakes to make. Is with chain rule. Misapplication of chain rule. So you got to be careful. Okay. So there's no other questions from there. We're going to get into section 3.5, which is like the next level of chain rule. It's a chain gang rule. No, it's what's called implicit differentiation. So the first good question would be, what the hell, in this case, does implicit mean? Right? So we have explicit versus implicit, like Hitchcock versus Saul, right? Or National Geographic drags it behind the bush and eats it. So we've been dealing with explicit forms of equations, functions. So explicit function will look like this. F of x equals x squared minus 2x. Y equals 3x plus 5. Even 7x minus 2 equals y plus 3x. Sure, why not? Over x. In the first two cases, it's solved for y. Y or f is explicitly a function of x. That's where that word explicit comes from. I have y equals stuff with x. The last one, it's not there yet, but I could easily get it there, right? I could solve for y. Here's implicit functions. It would look like I like it. I don't know why I used tangent twice, but who cares? Can you solve that for y? If you can, please do. And let me know. You guys understand what's going on? So if you try to start solving for y, there's y's in here. So you'd have to take an inverse tangent, right? You have to, arctangent or whatever you call it. But then you capture everything else. All the other y's get caught in there. And that's inside a thing. And oh, shit. There's just no way to, the minute you start to try to undo what's being done, you catch other y's inside what you just did to undo. So that is an implicit function of x. So I don't know. But so I have to assume that y is some function of x. I just don't know what it is. So let me take a slightly easier example. This is one of my favorites because it's very geometrically easy to tell what it's trying to tell you. What is this? The formula for it. Circle. And it is definitely an implicit function of x. But can you solve for y? No, I like that answer. No, you can't. But you can sort of solve for y, right? If you try to start solving for y, what do you get?
Square root of 1 minus x squared.
Careful. Plus or minus. That's the reason. So you don't get a function of x. You get two functions of x. So I can kind of work with this a little bit and show you why what we do makes sense. You cannot always do this, unfortunately. So here's the idea. Here's what implicit differentiation really says. And let me do this. Give me, I want to, before we jump into that, have you guys got all this here that you want? Real quick little side motivational work. Sounds weird. You can do it. If I had this function here, how would you take its derivative? Using a channel. So I could first rewrite this as
That quantity is going to give it 1/2.
good. Nothing's on the bottom, so positive 1/2. So then, what would its derivative be? Something to the 1/2. What happens?
1/2.
1/2 comes down in front of that thing to negative 1/2 times
8x
plus 5.
plus 5.
derivative of that thing, right? 8x plus 5, I agree. I'm going to stop right there for a second. You can keep going. But what I want to show you is, what if I had this? What if I had this function? How am I going to represent? I'm just going to represent like this. Let's see. Why not? How would you take its derivative? You do exactly the same thing as you did, wouldn't you? You'd say this is f of x to the 1/2. Right, so y prime would be 1/2 f of x to the negative 1/2 times f prime of x, right? So let me take it one step further. If I saw square root of y, remember f of x is just y, right? So y is implicitly a function of x. This is explicitly telling you what that function is. This is implicitly hiding from you what that function is, right? It's not showing you what it is. But the rule doesn't care. The rule doesn't give a shit. It just says this is what the rule says to do. So if I saw the square root of y, I could rewrite that as y to the 1/2. So the rule would say 1/2 y negative 1/2 times y prime. Because y itself is a function of x. Right? So a slightly better way would be leave this notation here, because I'm taking the derivative with respect to x. So at the end here, I get 1/2 y negative 1/2 dy dx. You with me? Dy dx is not 1. Whereas if I had square root of x, the derivative of that would just be, let me do it like this. D by dx. D by dx of this, what's the derivative of this? 1/2.
X to the
And then d inside dx, and of course this is 1. Okay, so the thing to realize here. Number one, I am, at the beginning here, we're so worried about process that I want you to understand, I still have to be explicit with what I'm taking the derivative with respect to. You with me? Because some of you guys might argue, you just said it a minute ago that we can't handle multiple variables, and now we got x and y playing with each other. It looks like frickin' multiple variables. But I have to be explicit about, am I taking the derivative with respect to x, or am I taking the derivative with respect to y? You with me? So unless otherwise stated, this is going to be derivative with respect to x here. Yeah.
So if you were to do that respective to
y instead. It would just be dx over dy.
Yeah, if I did this d by dy square root of x, it would look exactly like that except with x's. So it would be 1/2 x to the negative 1/2 dx dy.
Where would we see that?
Wherever it needs to show up. I mean, you have to realize the way that we orient our coordinate system and the way that we look at it and the way we define slope, it could have all been defined the other way. It could have been run over rise, right? Which wouldn't have matched with the physical world, but what does math care about that? Right? You guys, so this certainly is valid because x and y are just arbitrary variables, really, right? In a different situation, they might have the opposite relationship to each other. Or you could have entirely dr, ds, in which case there's no set, prescribed, traditional way of doing it. You just got to tell you which freaking way to do it. Okay. So, let's see what a real problem would look like here. Instead of just talking about the idea, let's get our teeth into something. I'm going to do a couple examples with you, and then I'm going to try to let you guys do one on your own. Let's go back. Oh, I left this guy and I erased him. Poor little dude. Let's do him. So when you implicitly differentiate, now I want you to realize something. If I have y equals x, what's the derivative?
1.
Tell me what the whole thing looks like.
Y prime equals 1.
Yeah, see, so I took the derivative of both sides, which makes sense. If I take the derivative of this side, I better take the derivative of that side. You with me? Of course, I got to make that very clear because that's exactly what we're going to do now. Whatever you do to one side, you better do the other side. Because I always get somebody to leave that 1 there. And of course, the derivative of 1 is 0. So it better become 0. Or else it gets a lot weirder than it's supposed to be. So what's the derivative of x squared with respect to x?
2x.
2x. Now what happens here? What rule do you have to use? Chain rule. That is a function of x inside the square function. Because that y could be 2x minus 7. And then it would be 2x minus 7 squared. And then I have to use chain rule, wouldn't I? Just remember, whenever you see y, it could be 2x minus 7, or your favorite function of x, whatever the hell it is. It could be that. So you have to use chain rule. So the derivative of something squared is
2y.
twice something good times
dy.
y prime, or dy dx. I like it. Either way you want to write it, it's fine. I just always default to this because I'm lazy.
So whenever we find y, we have to treat it this way.
Say again?
Said whenever we find y, we have to treat it this way, the derivative.
Whenever you implicitly differentiate with respect to x, when you're doing it to a y term, it's going to have a y prime attached to it. It's going to be that length, the chain rule, that y prime.
But here y is not with respect to x.
How do you know that? Of course it is. I desperately want you guys to realize it totally is. This is, in fact, go with me for a second. I'm going to come back to exactly that. Trust me. Okay. So what can I do? Now, what do you think my next thing to do would be?
Solve for y prime.
Solve for y prime. Right? So to solve for y prime, I just...
Bring over 2.
Yeah, I can kill the 2's for one thing, subtract the x,
X over negative.
divide the y. Is that cool? Okay, skipped a lot of steps, but they're easy steps.
What does it tell us, though, since the y is also both on both sides?
What's really awesome about that, I want you to realize, to remind me, this is the what?
Function.
What, geometrically,
Circle.
graphically. Circle with radius,
Of 1.
so it's otherwise known as the unit circle. So I got circle. For me, that's really good. So if I want to know the slope at some point, let's say a point that we all hopefully know. If this is 1/2, what's this going to be? Root 3 over 2. So I'm at the point 1/2, root 3 over 2. If I want to know what the slope is there, what's really cool is the derivative is a function in a way of both x and y. I can just plug the whole damn point in. So the derivative at that point would be negative 1/2 over square root 3 over 2, which is negative 1 over root 3. You guys kind of with me? And that would be the slope of the tangent line there. Makes sense that it's negative right?
Yeah.
Is that cool? Yes, sir.
So why that point when I had another point?
Because I can only do one point at a time. And it's a point that I know it's on there. All your sine, cosine pairs are points that are on the unit circle. That's, of course, how sine and cosine were first defined, right? But it could be any other point. It could be the point, I just got to figure out, if I was at the point, if x was negative 0.8, can somebody figure out what the y would be? Yeah, you just plug the damn thing in there, right? Solve for y. Of course, you're going to get two y's, but I can say I want the one up here. Are you guys with me here?
Yeah.
So when you have an implicit function, one that you can't solve for y truly, you can still figure out what the slope is. It's going to be dependent on both x and y. So you can just plug a whole point in. Yes?
But which point are we going to be working on that point? Yeah, but...
It depends. If they said find the tangent to the unit circle at the point 1/2 root 3 over 2, this is my m step, right? Finding my slope. So it totally depends on which point I'm interested in. This is the slope at every point.
Okay.
It actually is. It's pretty cool.
Only for that specific circle. Correct? For this?
Yeah, I mean, you can imagine. Now watch. Now, if I change this, what happens?
Nothing.
Nothing. If I change this to 2 billion, the first step is the same, right?
Yes.
Derivative of 2 billion is 0. Derivative doesn't care if you're big. You're flat, so screw you. You're 0, right?
If you would have a variable there instead of 1.
Oh yeah, definitely. That wouldn't be a circle. It'd be an entirely different function.
Here we took dy by dx. Can we take dx by dy?
Yeah, the really, you ready for this? This is one of the best things. This is dy dx, right? Equals negative x over y. What do you think dx dy is?
Negative y.
Negative y over x, and it's true. It's so nice. Right now, let's prove it. I like that you asked that question. That's awesome. So let's do this. Let's really bend your brain. So now I want to take the derivative with respect to y. Oh shit. So which thing is an implicit function of the other thing in this case? X is an implicit function of y. Now this is maybe pushing it, but we'll see. Because you got to get used to the idea, but the idea doesn't care which variable normally does it. It doesn't care if I want to do this way. So this is my this dy. So now, what's y squared derivative with respect to y? 2y. Right? Because then you get dy, screw it. That's just 1. Well, that's x squared with respect to y. It would be 2x
times
dx dy. I love it. And I'll put it like that because our prime is so ingrained that it means by x. I'll put it Leibniz notation, so it's not. And of course, that side is 0. Cool. So if you solve for dx dy, the 2's go away, subtract the y, divide by x. That is just so freaking nice that that's true. Because to tell you honestly, this is not truly like a ratio of things. It's actually a symbol that represents a derivative. This is a symbol. So it's so cool that we can actually multiply the dx up. We'll do that later. We can flip this dude. It's nice that it works that way. But it's truly not necessarily a ratio of those. It is in a way, but not really. It's just nice that it works that way. Yes, sir?
Is this particular derivative significant, like geometrically, or like to apply it or anything? Since it's just of the circle, like new circle?
Not really.
Like, what would dx dy, like, where would that be?
So just remember, it would be, so for this one, it would be negative root 3, and it would be the same exact line. It's just that it would represent the change in x over the change in y. So it's just, that's the run over rise. Right? It would just be going like that, basically almost, more than that, you got to flip that over, but it's the inverse coordinate system. Right? So instead of x, y, we'll have y, x. So I just got to flip it, and of course the circle didn't give a shit.
If plus or minus the square root of that function, that's the negative side?
No.
Okay.
That would be, we're talking about flipping coordinate systems down. That's a different. So let me go back to, how you guys feeling so far? I mean, the basic idea with implicit is sort of separate from some of the stuff we're doing up here. The basic idea with implicit is, if you're doing it with respect to x, y is an implicit function of x. So it's a chain rule problem then. You got to tack on a y prime. So you can almost reduce it to, anytime you see a y and you're taking a derivative, you better put a y prime at the end of that term. I really hope you can look at it more than just that, but that's, you know, your last resort to doing work. Okay. But let's remember that this was this here function, right? So let's look at this. Plus or minus just kind of float with us. So if I took the derivative here, and I can put the prime back, this is explicit. This is the explicit version of that, right? I have a warning on its CD check. Somebody appreciated that really bad. So I could rewrite this as 1 minus x squared.
Oh, it's 1/2.
1/2. Thank you. So what's the derivative?
You bring 1/2 down.
Plus or minus 1/2.
Just keep that inside. And then you do the inside, which is negative 2x. Oh, sorry, you bring the negative 1/2.
Good. Negative 1/2. The power goes down by 1 times
Negative 2x.
negative 2x. You guys all with me?
Yeah.
So now here's the thing you got to go with me for, and it's not even that big of a deal. This, I don't know if you've ever seen this. You see that negative?
Mm-hmm.
Wouldn't it change both those signs? So now it's minus plus. And the 2's cancel, right? So you get minus plus 1 minus x squared. Have you ever seen that?
No, I have not, sir.
But you actually have to be careful. I left my x out there.
Is it not the same thing?
Bad for me. Say again?
Is it not the same thing?
Not really. Not always. For us, that's the same thing. But it depends. Later, you'll see it depends on what's going
Oh,
on.
it's like adding a negative to it, so you're just...
Now, real quick. I'm not going to worry too much about the plus or minus. In this case, it doesn't really matter because it all matters on what you're plugging in there, which side you're on. So you have to pick the right plus or minus. I don't care how I put it there. Are you with me? Depending on if you're on the bottom half or the top half. How is it supposed to relate to this? How are they supposed to, and that actually, let me go back on what I just said. That is important, and you'll see in a second why. When I bring that back in, it becomes important. You'll see in a minute. How are these supposed to be related? Please, somebody answer.
Because the y right there equals that function which is on the bottom square. It's like the quotient rule.
All right, you're going too far for me, but I appreciate it. You went too far. These are supposed to be the same, right? Because they're both coming off the same freaking expression. You with me? Same equation. All right, and you guys are like, well, yeah, but I'll make sure everybody's... So these have to be the same, and they currently are not, but what is y?
Y is that inside function.
Y is this,
Yes.
right? Can I always do the no? So sometimes you're just not going to be able to check it like this, right? But in this case, I could solve at least to this point. So if I replace y with what it is, right, and I rewrite this a little bit, so I can bring this up, and when it interacts with the negative sign, it becomes this.
Negative.
And they are the same damn thing, right? Even down to the signs being in the right place. You guys semi with me?
Yeah. Yes.
So if you could solve for y in some fashion, and this is not truly solve for y, but it's solved enough to get the form, if you could do that, it should always agree with what you would get implicitly. Now notice, if I can't do that, I could never do this, because I couldn't get what y is. If I can't solve for y, I can't replace y with what it is, because I don't know what the hell it is. But I can still do derivatives on it. It's kind of cool. I don't have to solve for y. I can still attack it with derivatives.
So you had the plus minus on the bottom on the denominator. How do you bring it just because you can?
Well, this, and whatever the sign is, can always be put out front.
Okay, yeah.
And then plus or minus times negative is minus plus. Good. Okay. It still is not all that important here, but I still want to expose you to this, because it does become important later, which way it is. It might be dependent on, it might be something to do with a pattern that I see, and if I have it the wrong way, it's not going to work right. Believe it or not.
This equation is explicit, right?
Yeah, this is an attempt at an explicit form. It still isn't officially, because it's got two parts to it. So but this is explicit enough for me to be able to do this check work. This is the idea of implicit differentiation. This is something you can do sometimes, just to check it, and then you can plug that into there to see if they do agree. Because they have to agree. They both started at the same damn place. Yes, sir?
So if you were to go with the explicit part, if you were to go and switch the x and the y, you would get the dx over dy?
No, if I were to, instead of solving for y, solve for x.
Okay.
I don't know if that's what you meant, but yeah, you're right, because I'd end up with the same form.
Okay.
But what I'm really doing is solving for x. Do all this, I'd end up with this. Cool.
Such a good question.
Okay. Let's try some more. Maybe a little more complicated than that. Let's see. Here, you guys see how far you can make it on this. Implicitly differentiate this, please. Oh. Before I forget, there's a quiz Monday. Up through section 3-4.